Welcome to the lesson on springs. In this lesson, we'll be discussing Hooke's law and another form of mechanical energy called elastic potential energy. Let's start off with an animation showing the concept here of Hooke's law. Hooke's law in equation form is Fs equals negative Kx. Why the negative, you might ask? Why is the negative in front of the Kx? More on that in a moment. First, let's take a look at a spring being stretched and all the variables that are taken into account. Okay, here we are with three identical springs, and we're going to take and attach different masses to each one and take a look at what's going on here. Each of these springs with no mass attached would be said to be in equilibrium, with this dashed line representing equilibrium. So if we go ahead and attach the 50-gram mass to the first object, we can see it bounces up and down a little bit, but once it comes to rest, it has stretched the spring from the 30-centimeter mark to about the 35-centimeter mark. So we would say the X value, or the stretch of the spring, is 5 centimeters. The stretch or compression, the X value, is always measured from the equilibrium position. If we hang 100 grams, as expected, double that mass, twice the stretch, has stretched us out to 10 centimeters. 250 grams, which is 5 times the original amount over here, gives us a stretch of about 25 centimeters, as opposed to the 5 by the 50 gram. So you can see already we've got some kind of direct proportion relationship going on here, and that's where Hooke's law comes from. The force stretching the spring in all three cases here is equal to the weight being hung, and each spring is identical and has the same what is called spring constant. More on that, and back to our lesson. So where did this concept of Hooke's laws come from? Robert Hooke attached masses to various springs, like we just showed in our animation. And what he did was he graphed the force stretching the spring on the y-axis and the amount by which the spring was stretched or compressed on the x-axis. In this case, the amount that it was stretched. And he noticed that as he did that, if he didn't ruin the integrity of the spring, that he got a linear fit on the data of Fs versus X. Well, of course, what does this indicate? That the force stretching the spring is directly proportional to the stretch of the spring. Because it's a linear fit, the slope is known as the spring constant, and it's denoted by lowercase k. Back to our question up here, why is Fs negative? Fs is negative because it is a restoring force. It is always trying to restore the object, the object back toward equilibrium. So if you want to think of it this way, the stretch is always an opposite direction. The force is always an opposite direction of the displacement of the stretch itself. So if the stretch is downward, the force is trying to restore it back up. If the compression were upward, then the force would be restoring it back down. And because they're always in opposite directions, that's why you see Fs equals negative Kx. Many times, honestly, we get lazy and we just write Fs equals Kx, and that's okay in certain contexts, as long as we remember that Fs is a restoring force. Okay, next we have the third form of mechanical energy that we're learning in a course, and this is elastic potential energy. This is, of course, the energy stored when we, in this particular case, stretch or compress a spring. Again, it's the third form of mechanical energy, joining kinetic and gravitational potential energy. So we no longer can say when we do problems, oh, potential energy, we have to be specific about which kind. And elastic potential energy has as its equation, and then it comes from the work energy theorem. It's a derivation where US, and that would be a denotation for college physics, it would be PES in Regents physics, equals 1/2 kx squared. Okay, don't forget to square your elongation when you go to calculate elastic potential energy, or often referred to as potential energy stored in a spring. That's why the S subscript. And just like all other forms of energy, this energy has the units of joules. That'll do it for our introduction on springs. Much more to come as we tackle problems in class, and we'll address all these concepts and see them again.